So welcome back everyone. So the topic of today's video is Newton's laws of motion. And we'll take up some problems from the book Pathfinder. So the first question is a pulley mass problem. So in this setup, the string is inextensible and light. There is no friction at the axles of the pulley, but there is friction between the string and the pulley's wheels, and it is enough to prevent slipping. Now all the pulleys are light except the pulley capital P, and which is this particular pulley over here, which has whole of its mass m concentrated in its axle. So this line is kind of important. So basically, if we try to visualize this pulley over here, there is no mass away from its axles. Almost all the mass is concentrated at the axle itself, or the center of the pulley. Initially, the block B of mass capital M is on the ground, and the block A is held at rest. How much minimum mass should the block A have so that after releasing it, block B starts rising? So they're asking how much minimum mass should we hang over here so that this block on the ground starts to rise. Okay, so give this problem a try, guys, then check out the solution. Okay, so firstly, let's start focusing on the pulley P. So here it's given that all of the mass is concentrated at the axle. So the moment of inertia about the axle, this would just be equal to 0. Why? Because there is no mass away from the axis, right? So if you just do sigma mi ri squared, away from the axle, there is no mass. So the moment of inertia about the horizontal axis passing through the axle will actually become 0. So what this directly means is that if you figure out the net torque about the axle, this just has to be 0. So now what are the forces acting on this pulley? So firstly, we have the tension force and mg. So they both contribute no torque about this axis because their line of action directly passes through the axle, right? Now let's say we section the string at these 2 points. So the tension at these 2 points will become external force for this pulley, right? So let's say the tension on the left string is T1 and on the right string it is T2. So the torque because of this tension T1 and the torque because of this tension T2 are the only external torques acting on the pulley. So which means T1 times R should be equal to T2 times R if we want the net torque to be equal to 0. Okay, and here R, I am assuming the radius of the pulley. So what this means is the tension on the strings on either side of this pulley should be the same. Okay, so T1 and T2 are the same. So let's just call them as T. Tension, as the string tension over here is T, the string tension over here will also be T. And this is by using the same exact argument because the moment of inertia about this axis is 0, which means T1 into R should be equal to T2 into R. So even these two tensions have to be the same. Okay, so which means the tension over here should also be T. So now if we draw the FBD of the pulley P, let's just say it is moving down with an acceleration of A. So the forces on it are the force of gravity, mg, and it has 2T pulling it downwards and T pulling it upwards. So that would be just T pulling it downwards. So from here, by writing Newton's law, you can get A equals G plus T divided by M. So now what this means is the acceleration A is clearly greater than G. So the pulley is clearly going to accelerate downwards and its acceleration is going to be greater than G. The only other possibility is when T equal to 0, that would mean G is 0. That would just mean that the pulley is free falling. Now let's talk about the block A, and let's say its mass is Ma. So the force of gravity acts downwards of mag, and then we have the string tension T, and the acceleration of the block, let's say it is B. So from here, B comes out to be G minus T divided by Ma. So if I call this equation as equation 1 and this is equation 2, if you add these two, what we get is A plus B equals 2G. So now if we look at the pulley for a second, the center of the pulley is moving down with an acceleration of A, and the string on the left end is moving down with an acceleration of B. Now, if the string on the left end is moving down with B, then that means the resultant acceleration at this particular point on the pulley is also B downwards. Okay. So now let's say the other end of the pulley is moving up, has an acceleration of A dash in the upward direction. Okay. So now here we have a result that the acceleration of the center of the pulley is the average of the accelerations on the ends. Okay, the proof for this is just simple. So basically, relative to the pulley, we should only see a rotational motion, right? So if we go relative to the pulley, we'll subtract A from both of the ends. So this end will move up with an acceleration of A, and this end will move down with an acceleration of B minus A. Okay, now as we are observing with respect to the pulley, we should only see a rotational motion, which means it should have some alpha, which means we can write R alpha equals A dash plus A and R alpha equals B minus A. So these both have to be the same, right? So A dash plus A should be B minus A. And from here we'll get A dash as B minus 2A. Okay, or what you can do is you can take the average of these two. So as A is downwards, we'll take the downward direction as positive. So B minus A dash by 2 is the average, and this should be equal to A. Okay, it's the same thing basically. Once we determine A dash, if you observe, A dash is the acceleration of the right point, right? So this is the acceleration with which this part of the string is moving up. So consider all these points lying on this string. They're all moving up with an acceleration of A dash. Okay, so now if you consider this part of the string on the top, right, all these are moving down with the same acceleration as the center of the pulley, right? And the pulley was moving down with an acceleration of A, which means these points connected to the right part are going to move up with the same acceleration of A. Okay, otherwise what will happen is this part of the string will break, right? As it's an inextensible string, the acceleration with which this point moves should be the same as the acceleration with which this point moves down. So now let's observe this particular pulley over here that is directly above this block B. So here the end on the left has an acceleration of A dash, which we determined as B minus 2A, and the end on the left has an acceleration of A, which means the center of the pulley has an acceleration of the mean of these two, which will be B minus A divided by 2 in the upward direction. Okay, so now let's eliminate B by using this equation. So this is going to be half of 2G minus 2A. So this is the acceleration of the center of this pulley, and this comes out to be G minus A in the upward direction. Now here we have to make an observation. Our initial finding was that the acceleration A should definitely be greater than G. Okay, but here they're saying here after solving, we get the acceleration of the center of this particular pulley over here. It's coming out to be G minus A. So if we want this to be positive, then A has to be less than G, right? So what that means is clearly the center cannot have an acceleration, which means AC definitely has to be 0. So which basically means AC would definitely be equal to 0, which would give us the answer for A as equal to G. And if A equals G, then we get B equals G as well. Okay, so from here, so A and B are both equal and they are both equal to G. So now if we go back to our original diagram, then what will happen is acceleration of A is going to be G. The pulley is going to free fall as well, which means even this end has an acceleration of G downwards. Now if this end has an acceleration of G downwards, this end, the right end, will have an acceleration of G upwards. Okay, so this is how the motion is going to look like. So if you observe this pulley over here, it is a non-rotating pulley, right? Its center, if you observe with respect to the center of this pulley, the ends have 0 acceleration, because the G, if you subtract G from both of these ends, they cancel out, right? So this is a non-rotating pulley. But if you observe this pulley B has an acceleration alpha in the counterclockwise sense, right? And that alpha just comes out to be G divided by R, where R is the radius of this pulley. And similarly, even these two pulleys are going to be rotating pulleys because of the no slip condition, right? So the other 3 pulleys except P is going to be rotating, or basically it's going to have some angular acceleration, whereas this particular pulley is a translating pulley. It's just translating downwards with an acceleration of G. So now if we check the options, so in the options, in option C, they're saying whatever mass the block A has, block B will not rise. So that would be correct, because AC greater than 0 was a physically impossible situation. So it will never happen. Now pulley P moves downward without rotation, which is true, while wheels of the other pulleys rotate. Okay, so this would also be correct. Okay, so that was it for this question. So the answer will be C and D. Okay, now let's move to the next one. Okay, so the next question is MCQ 2. So in the setup shown, a thread is tied between nail A and on the wall and nail B on the inclined plane as shown in the figure. You can change the length of the thread by changing the location of nail B. So which means the height from the, this vertex is actually constant, whereas this end B can be moved along the incline, meaning the length AB can be changed. A bead can slide on the thread without friction. It is released from the nail A. What should the length of the thread be so that the bead reaches the nail B in the shortest time? Okay, so the goal is to minimize time here. So the direct approach could be that we find out the length AB, okay, and maybe just figure out what this angle alpha is in terms of geometry. And then the time period is going to be root of 2LAB by G sine alpha. Okay, this as a function of alpha, and we'll differentiate and make it 0, right? So that would be the calculus approach. We're going to look at a slightly different approach in this video. So before moving to the question, we'll discuss a simple result here. So let's say we take a circular frame, okay, that is fixed, and it is lying in the vertical plane, meaning gravity is acting downwards. And from the top of the circle, I'm going to connect it to some other point with the help of a string, let's say. So this is basically a chord of the circle, right? And then I'm going to connect it to some other point. Let's call this point as point 3. Now let's say I release a bead from this point 1 and let it slide along the string. I'll do exactly the same with the bead and make it slide along the path 1, 3 as well. So the claim is that T12, which is the time to go from 1 to 2, is the same as the time to go from 1 to 3. And in fact, this is going to be the same for any particular chord that you draw on the circle, okay? So the proof of this is quite simple. So let's locate the center of the circle. Let's say it's somewhere over here. Connect it to point 1 and 2. So this would be the radii. So let's say this is the vertical line, right? So if I say this angle is alpha, this angle will also be alpha. Now if I drop a perpendicular onto the base, onto the line 1, 2, the length 1, 2, I can see it is 2r cos alpha. The component of gravity along the incline is going to be g cos alpha, right? Because if the incline made an angle of alpha with the horizontal, we know the acceleration is g sine alpha. Here I'm taking the angle alpha with the vertical, right? So it's going to be g cos alpha downhill. So acceleration in the 1, 2 direction is g cos alpha. So now we can directly apply the time relation, which was square root 2L by G, right? So here if we apply it, it's going to be square root 2 into 2R cos alpha over G cos alpha. And here if you observe, it turns out to be independent of alpha. So the time turns out to be square root of 2 times the diameter of the circle divided by G. So here we observe two things. First is that the time actually depends on how large the circle is, which is quite intuitive. If you take a larger circle, it'll take more time to cover the length of a chord. And another thing that is not so intuitive is that the time turns out to be independent of alpha, meaning whatever angle, whatever chord you take from this point 1, all the beads are going to reach the other end in exactly the same time. Okay, so yeah, we're going to use this particular result in this particular question. Okay, so before we begin, so let's see what are the fixed quantities. So the height of A from the ground is h, and it is fixed. So this height over here, which is h, this is actually a fixed quantity, and the point B we can take anywhere on the incline. So let's say it's somewhere over here, and this angle over here is theta. So now if I consider this AB as the chord of my special circle, then, and let's just try to draw a circle passing through these 2 points, something like this. So if this is my special circle, so the time it takes to go from A to B will be equal to square root 2 times the diameter of the circle divided by G, right? So basically if we want to minimize that time, so basically if our goal is to minimize time, then what we should do is, we can always imagine a circle, right, passing through A and B. So what we should focus on is how can we minimize the diameter of the circle. So the thing is, can we draw a circle that is smaller? So let's fix the point A at the top of the circle, just like we did in the proof of this result, and let's make the circle bigger. So if you observe, the intersection of this circle with the plane is somewhere over here. So this will be the chord AB, right? Now let's say we make the circle a bit smaller, because that's our goal, right? So we made the circle a bit smaller, and if we say this is our point B, then the thing is, if we compare the time between the first case and the second case, clearly the second case will have a smaller time. Why? Because the radius of the second circle is smaller. So now the question is, how far can we go? How small can we make the circle? And the answer to that is when this circle becomes a tangent to the plane, right? Because after that, we can't draw a chord that reaches the plane, right? So the minimum will be when the circle becomes a tangent to this plane. And if we connect it to the intersection point, right, this is the smallest possible circle that we can draw, which means this is also the circle, which means this is the particular case AB for which the time will be minimum. Now, as the diagram doesn't look so good, what I'm going to do is I'm going to make this point A a bit higher so that the diagram looks a bit more clear. Okay, so all I'm doing is modifying the diagram a bit. I'm saying A is somewhere over here. So now let's say the center of the circle is somewhere over here. Now, as the incline is the tangent to this circle, if I draw a line from the center, it will be perpendicular to the plane. Why? Because the incline is the tangent and this line over here is the normal, right? So the angle between these two lines will be 90 degree. Now the angle between the incline and the horizontal is theta, which means the angle between the normal and the vertical will also be theta. So this particular angle is going to be theta. Okay. So now this is a property of circles. If this angle is theta, this will be theta by 2. Okay, this you can prove pretty easily. If this is theta, this will be pi minus theta. So the other two angles are going to be theta by 2. Okay, so now the question wanted you to find this length AB, which is just going to be, so the length AB, we can see, so the radius of this part, I'm going to call it as A. So this is going to be 2r cos of theta by 2, right? So just drop a perpendicular. This will be r cos theta by 2. This length will be r cos theta by 2. So the total length is 2r cos theta by 2. Now the thing is, we don't really know the radius, right? So we have to eliminate that. For that, we know the height. This particular height over here is actually h, right? Okay, so for that, what we can do is, so let's call the vertex point as point D. The length AD, we know it is h. The length AC is the radius. So the length CD is going to be h minus the radius, right? And now this length over here is equal to the radius, right? Now from here, we can see a right triangle, right? And this right triangle, the base is capital R and the hypotenuse is h minus r. So if I find the cos theta, so this comes out to be capital R upon h minus r. And okay, and after putting it in, what I did is I brought this cos theta to the numerator after taking the LCM, and 1 plus cos of theta is a trigonometric identity. We can write it as 2 cos square half the angle, right? And you cancel out 1 cos theta by 2. And finally, we get this as the answer. And that would be option D. Okay. Now, if they had asked the value of the time, for that, what we can do is the gravity along this string AB is going to be g cos of theta by 2. So now we can just do square root 2h by g, right? We know the length AB. The length AB divided by the gravity, which is g cos of theta by 2. And the under root of this. So this is the minimum time that the bead takes to go from A to B. Okay. Okay. So now let's come to the last question. So this is question number 24 from the check your understanding section. And now the question is saying a disk whose radius is r, it is inclined at an angle of theta with the horizontal. So basically we can imagine this like an incline of angle theta and a disk that is kept on the incline, and it is rotating. Okay, we can imagine the situation something like this. So basically, the gravity along the incline felt by each of the sand particles is going to be g sine theta, and it is going to feel a gravity of g cos theta in the normal direction. So from the side view, so let's say from the side view, this is the disk and this is the rotation axis. So the g sine theta is going to be something like this, and the cos component of gravity is something like this. Okay. Okay, so now let's continue reading. It is evenly covered with a thin layer of sand. Okay, so there is sand on top of the disk and it is evenly covered. So the coefficient of friction between the sand and the disk is mu. The disk is made to rotate about its central axis of symmetry with gradually increasing angular velocity. So for very small angular velocity of omega, the sand will actually rotate with the disk because the friction is making them rotate. Okay. So, and omega is gradually increasing. The angular velocity is increased so gradually that the tangential acceleration of the sand particle is practically negligible. Okay, so basically d omega by dt or alpha is, just assume it to be 0. What is the angular velocity of the disk when when eta fraction of the sand has fallen off the disk. Okay, so we'll slowly start increasing the omega, and we know that some of the sand particles will start flying away. So finally, when eta fraction of the sand has fallen off the disk, we have to figure out at that instant what is the angular velocity. Okay. First of all, guys, I want you to imagine the disk as an inclined plane. So basically, if you stand on the disk, then you will feel an mg sine theta along the slope and an mg cos theta and a normal reaction which is equal to mg cos theta. Okay. So now the thing is, it is a rotating disk. Now let's just consider a sand particle somewhere over here. So it's going to feel mg sine theta. Now, and in the rotating frame of reference, we can give this a centrifugal force. So it's going to feel an m omega square r. And then there's going to be friction, right? Now at different points, the F bead is going to be slightly different. So if the particle was over here, then the centrifugal force will be in this direction, radially outwards. But the mg sine theta is still going to be downhill. And the friction force will be in such a direction so that we can balance out all the forces, right? So now the important question is, what is that particular location on the disk at which the sand particle has the highest tendency to slip? Okay, so let's try to investigate that. So we are trying to find out what is the point on the disk at which a sand particle has the highest tendency for slipping. So in other words, we have to find out where is the friction needed the maximum. So here if you observe, friction has mg sine theta as a friend to balance out m omega square r. So if you think about it a bit, the point where the tendency to slip is highest is at the lowest point on the slope. At this point, what happens is mg sine theta is once again downhill, right? And the centrifugal force is also in the same direction. So which means friction is in the minus r cap direction. So friction has to fight both mg sine theta and m omega square r in this location. Okay, so basically the bottommost point over here is the point where the sand particle is just about to slip. So let's call this point as point A. So the answer is going to be point A, because point A is the point at which we need the highest friction. Okay guys, so now what we are going to do is imagine the disk is almost completely filled with sand. Okay, and none of the sand has slipped. So we slowly start increasing the value of omega. There will come a time where the sand particle starts to slip. So where will it slip first? It will first slip at point A, right? Because point A needs the highest friction. So let's try to figure out the friction force needed. So at this particular time, let's say the omega is omega 1. So let's say at this time, the omega is actually omega dash. Okay, so let's say that corresponding value of omega is omega 1. So once again, mg sine theta acts mg sine theta and m omega square act in this direction opposite to f. So friction force should be equal to mg sine theta plus m omega square r. Now when it is on the verge of slipping, friction force becomes mu mg cos theta, right? Because once again the normal, if you look from the side, the gravity normal to the plane is g cos theta, right? So the normal reaction will be mg cos theta is going to be mu mg cos theta equals mg sine theta plus m omega squared r. So now let's solve for omega square. So if you observe, so this is the value of omega that we get. Now once the omega is being increased slowly from 0. So once the omega reaches this particular value, a small dm mass of the sand at the periphery of the disk at this lowest point will slip. After this, we'll reach the limiting case, and once we increase the omega by even a little bit, this dm mass will slip. Okay, so the friction is only limiting at this point, guys, because everywhere else the friction is still static, right? When omega reaches this value, the bottommost sand particle slips. So what happens is, so let's call this omega as omega 1 itself. So let's say we rotate the disk with the angular velocity of omega 1. So let's just only talk about the periphery first, right? So there is going to be dm masses that are laid out on the periphery of the disk. What will happen is, if we rotate it with an angular velocity slightly greater than omega 1, the moment all these dm masses reaches A, it will fly off. Okay, so after some time, this dm mass will reach here and it will fly off. And similarly, this dm mass will reach here and it will fly off. And slowly what will happen is all the sand particles on the periphery will fly off. So the main idea is that the sand is removed from the circumference of this disk. So let's say this represents the border of the sand in the initial situation. Then basically after some time, what will happen is the radius shrinks something like this. Okay, and it will still be a uniform circle. So now the question is, why isn't the point on the inside slipping? And the reason for that is the inside point, at an inside point, the required centrifugal force is lower, right? So this point m omega square r2, here r2 is less than r, right? So the friction here required will be smaller. So that we can even observe from the limiting omega expression, right? So for a, like if we set r equals r by 2 here for example, which gives us the limiting omega for a sand particle at a radial distance of r by 2 from the axis, right? So for this case, so if I put r equals r by 2, we can see that the omega is greater, right? It is root 2 times greater. So basically once we increase it slightly by omega 1, all the sand particles present at small r equals at the periphery will go away. Okay, so now in the problem, the initial radii of the region in which the sand is present is small r, and the final region, let's say, has a radius of small r. Now it's given to us that eta fraction of the disk has fallen off, which means the ratio of this area to the total area is eta. So eta is going to be pi times capital R squared minus small r squared divided by pi capital R squared. Okay, so after solving, we'll get small r as square root of 1 minus eta times capital R. Okay, so now we need the omega when the sand radius is smaller. Okay, so at this particular situation, the sand particle at the bottommost, so let's say this is the top view and this is the bottom of the slope. So the sand particle at this point is at the verge of slipping, right? So let's say the angular velocity of the disk is omega 2. So the omega 2 in this sense is just the omega limiting, right? Omega limiting when small r equals this particular value. So let's try to solve for this. So it will be g times mu cos theta minus sin theta. So when omega becomes equal to this particular value, the sand particle that is present at the lowest point will be on the verge of slipping. So now if we start increasing the omega even more, the radius will start shrinking even more. Okay, so yeah, this would be the answer to the question. So that's it for this video, guys. If you have any doubts, you can comment down below. And if you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.